For more than 200 years, astronomers have been carefully charting the countless small worlds scattered throughout our solar system. Every asteroid, every comet, and every faint moving speck of light had to be discovered individually, observed repeatedly, and assigned a precisely calculated orbit before it could officially become part of our cosmic map. It was a slow and meticulous process that remained largely unchanged for generations. Then everything changed. High in the Chilean Andes, the Vera Rubin Observatory opened its enormous eye to the night sky, introducing a completely new era of astronomical discovery. Even before its ambitious 10-year legacy survey of space and time officially began, the observatory was already transforming planetary science. During early engineering and calibration observations, the telescope collected a test dataset that immediately captured the attention of astronomers around the world. That preliminary survey contained nearly 1 million individual measurements. Within those observations were more than 90,000 previously known solar system objects, along with over 11,000 completely new discoveries that had never been recorded before. The numbers were astonishing. The true surprise wasn't simply that the observatory was powerful, it was what those discoveries revealed about how much of our own solar system still remains hidden. If more than 11,000 unknown objects could be uncovered during nothing more than engineering tests, how many millions of undiscovered bodies are still waiting beyond the limits of previous surveys? How much of our own celestial neighborhood has remained invisible simply because our instruments were never capable of seeing it? The answer lies in the revolutionary design of the Rubin Observatory itself. At its heart is the Simonyi Survey Telescope, equipped with the largest digital camera ever built for astronomy, a remarkable 3.2 gigapixel instrument engineered specifically to observe enormous sections of the night sky with exceptional detail. Weighing nearly 3 metric tons and built around 189 highly sensitive CCD sensors, the camera records an area of sky roughly 45 times larger than the apparent size of the full moon in a single exposure. This gives the observatory an extraordinary advantage. Traditional telescopes usually force astronomers to choose between two options: examine a tiny region in great detail or scan a wide area with much lower sensitivity. Rubin does both at the same time. It can rapidly move from one target to another within seconds while collecting an extraordinary amount of information, generating nearly 20 terabytes of raw observational data every single night. When astronomers processed the observatory's first engineering images, they found far more than spectacular photographs. The telescope captured breathtaking views of famous regions such as the Trifid and Lagoon nebulae, along with the crowded galaxies of the Virgo cluster. Yet some of its most revolutionary discoveries appeared as tiny moving points of light crossing those images. Those faint dots represented previously unseen members of our own solar system. During its early commissioning phase, the observatory identified more than half as many new asteroids as the entire worldwide asteroid discovery network typically finds over the course of an entire year. But Rubin is doing far more than simply counting space rocks. By tracking enormous numbers of asteroids with incredible precision, astronomers are constructing an increasingly detailed map of the gravitational structure of our solar system. The telescope has even recovered several asteroids whose orbits had become uncertain after years of limited observations. This dramatic leap in detection capability carries enormous importance for planetary defense. Among the newly discovered objects were dozens of near-Earth asteroids. Fortunately, none of these newly identified bodies currently pose an impact threat to our planet. However, they reveal how many potentially important objects have remained undetected until now. For decades, astronomers have considered asteroids measuring roughly 140 meters across to be especially significant. An object of that size would not threaten human civilization as a whole, but it could devastate an entire metropolitan region with destructive power comparable to an enormous nuclear explosion. Although NASA was directed to identify at least 90% of these potentially hazardous objects, That goal has remained incomplete for years. The Rubin Observatory was specifically designed to help close this gap. Current simulations indicate that throughout its decade-long survey, the telescope could discover tens of thousands of additional near-Earth objects, dramatically improving our ability to identify future hazards well before they become dangerous. That capability could prove invaluable. Planetary defense systems, including technologies demonstrated by NASA's DART mission, are only effective if threatening asteroids are discovered many years before a possible impact. The greatest danger is not necessarily the asteroids we already know about. It is the enormous population that has remained hidden until now, quietly traveling through our cosmic neighborhood beyond the reach of previous surveys.